Okay, another important application of stoichiometry is in a process called limiting reactants or limiting reagents. And it's really actually kind of an intuitive thing. It's really just that if you react two things together, if you're doing a chemical reaction, then in general, you're going to run out of one thing faster than you run out of the other. So you're going to use up one component faster than you use up the other. And that's just generally true for things, right? You kind of overestimate on one of the things and you just use up what you can. And then that one thing that you're using up is going to limit the formation of the product. So we call that a limiting reactant or a limiting reagent. So let's think about this kind of from a conceptual standpoint. Let's think about bicycles. If I was thinking about a bicycle as kind of a chemical process here, which is a little bit silly, but that's okay. But, you know, if we have one frame and two wheels and that makes us bicycle, and I have three frames and four wheels, how many bicycles can I make? Well, you probably look at this right away and you say, well, I can make two bicycles, right? You've been thinking in this way since early on. You know, this is a really common way of thinking about kind of proportions. It's a common way of thinking about kind of numerical sense. So you know that it's two bicycles, but what you did kind of intellectually, if we're bringing this back to processes of dimensional analysis and skills that we've been practicing in chemistry classes, what you essentially did is you did some unit conversion. You said if I had three frames, and I have a ratio of one frame that gives me one bike, right? Because it's kind of, here's my chemical process, it's a 1-to-1 ratio. Then that means that with those three frames, if I had as many wheels as I could possibly have, that would give me three bikes. That was your thinking for the first part. And then you said, well, I have four wheels. And for every one bike, I need two wheels. So again, setting it up with my dimensional analysis here to divide out my units and give me units of bikes, then that gives me two bikes. And you said, well, of those two then, with these component pieces, I can make a maximum number of two. I can't make any more than that. I'm going to have some leftover frames though. So we would say that the frames are in excess because we have extra of them, and that the wheels are my limiting reactants. So that's going to limit how many bikes I can make. And then this number of bikes is the maximum number of bikes I can make. Okay, pretty straightforward. So like I said, you can look at this problem and you can solve that. You can do the mental geometry, the little mental gymnastics maybe to get to this answer. But this is really what you're doing. This is the process and kind of formalizing it. And so now we have some terms and some language. Now let's put this in the context of a chemical reaction because we're chemists and that's what we do. So if I have a chemical reaction that looks like this, so I'm looking at solid aluminum reacting with potassium hydroxide and giving me aluminum hydroxide and potassium left over. Now it's saying if I react this many grams of aluminum and this many grams of my potassium hydroxide, what is going to be limiting in the formation of my aluminum hydroxide? So in these problems, when we're thinking about the stoichiometry process, I'm going to be given information about two thing ones, which means that both of these are my thing ones, or A or B, or however you want to think about them. So these are both thing ones, and thing two is what it's asking the question about. What is the limiting reactant in the formation of this guy? So this is thing two. Now, because I have two thing ones, I have to do the same setup I did with the bike. I have to figure out if I have that much of my aluminum, how much of this can I produce? And then I'm going to say, well, I have this much of my potassium hydroxide, how much of this can I produce? And then whichever produces less, then that's going to be my limiting reactant. So I have to do two parallel stoichiometry problems, which is excellent practice. And we know that stoichiometry is going from thing one to thing two, and we're going grams to moles. So we're going to go grams of aluminum to moles of aluminum, moles to moles. So I'm going from moles of aluminum, that's my thing one, to moles of aluminum hydroxide, because that's my thing two. And then I'm going from moles to grams. So I'm going from moles of aluminum hydroxide, that's my thing two, to grams of aluminum hydroxide, because that's going to give me a maximum mass potentially for how much I can produce. Okay, so there's my setup there. Now I'm going to fill this in from the periodic table. So in every 1 mole of aluminum, when I look in the periodic table, it's 26.98 grams. That's just the molar mass of the aluminum itself. The molar ratio comes from the balanced chemical equation. This is a 1-to-1 ratio. So for every 1 mole of aluminum, I produce 1 mole of aluminum hydroxide. And now I go to the periodic table again. For every 1 mole of aluminum hydroxide, I do aluminum, 3 times my oxygen, 3 times my hydrogen, and I end up with 78 grams. And now if I run my numbers, grams to moles, moles to moles, moles to grams, then I'm left with an answer of 20.6 grams of aluminum hydroxide. Okay, now just a couple features here. I am being very specific about my units. Remember with stoichiometry, it's important to always label not just grams, but grams of what, because we're going from grams of one thing to grams of another thing. So it's important to be really specific with your units. And am I even done with my problem? No, I'm not done with my problem. This is just how much I'd be able to produce from this, but I also have this much of my potassium hydroxide. So let's figure out how much we can produce from that. We're going to do the same process again, but with a new thing 1. My new thing 1 now is my potassium hydroxide. So it's the same setup, but I need a new molar mass here. So let's go from grams of potassium hydroxide to moles. Moles of potassium hydroxide, here's my new thing 1, to moles of aluminum hydroxide, that's my thing 2. And now I'm going from moles of aluminum hydroxide to grams of aluminum hydroxide. And let's check my setup here. Grams to moles, moles to moles, moles to grams. Good. All right, now if I go to my periodic table, then I take, for 1 mole of potassium hydroxide, I need the mass of potassium, oxygen, hydrogen. I get 56.11 grams. This molar ratio comes from my balanced chemical process. So for every 3 moles of potassium hydroxide I produce 1 mole of aluminum hydroxide. And then I've already calculated this from step 1, so I can use that same number. Hasn't changed in the time that I've done this problem. At least I hope not. And now I can run the numbers again. I'm going to be limited to 3 sig figs with my starting amount here. And I get 5.05 grams of aluminum hydroxide. Okay, so just like the logic of my bicycles, the first question here is, what is the limiting reactant? The limiting reactant is the one that is going to limit the formation of the product. So whichever one makes the least amount of product is going to be my limiting reactant. And then whatever's left over is going to be an excess. It didn't ask for that specifically, but this is just to remind ourselves of the concept. So we have excess aluminum. We're going to have some aluminum left over at the end of it. We could actually calculate how much is left over, but we'll kind of save that for the later days. So here's my limiting reactant, and then it says, well, what is the maximum mass I can make? The maximum mass is if I use up all of this, which limits my process, this is the maximum amount I can make. Just like with our bicycles, right? I could make 2 bicycles because I was limited by my wheels. Okay? All right, so if you have any questions on this, don't hesitate to reach out. Limiting reactants is really important for experimental chemistry and for figuring out kind of what you can produce in the lab and by how much and how much you can possibly produce when you scale things up in industrial processes. So super important, and I'll talk to you again soon.